Okay, breaks over. All right, so serious business. Okay, all right, so yeah, so we'll see some applications of this method next. Okay, so I'm largely going to tell you about. Well, actually, it seems like I won't even tell you about two, because I'm going to tell you about 4 query locally decodable codes. It's the same as, like, telling you about 4 XOR instead of 3 XOR. But anyway, okay, so I'll tell you about like lower bounds on locally decodable codes next. And it seems like I would likely not have time for the LCC business, but if I get there, I'll at least try to tell you about the polynomial concentration business. Okay, good. All right, so this is like an entire switch. So, it's intentional, because now we're in the application phase, so we're solving problems that other people care about. Okay, so if you're an algorithms person and don't care about coding theory, that's okay. Okay, just like go with the flow. So let's recall like basic coding theory if you were not somehow here for the last week's workshop. Otherwise, this is going to be very easy. Error correcting codes, right? They map k bits into n bits. I'm going to look at binary codes. They add redundancy. And what's the goal? Well, you're going to get like some corrupted version of this code word, let's say with delta fraction bits corrupted, and you still want to somehow get back the message. This is standard coding theory. Right now, we are going to care about codes which admit a especially simple decoding algorithm. Okay, we are going to call this algorithm local decoding. And the way you should think about it is, because I'm imposing additional restriction on the decoding algorithm, because I want it to be extremely simple, it actually imposes a higher bar. It makes the task of constructing such codes more difficult, because I want not just arbitrary good codes, I want codes which can be decoded by the simple algorithm, right? So that's like how you should think about it. So it's like an exotic object we are looking for. We're looking for like a code which admits an especially simple decoding algorithm. Okay, what kind of algorithm is this? So a usual decoder gets a corrupted code word y. You have some guarantee that the Hamming distance of y from some code word is at most delta, and all my distances are normalized Hammings, which means the fraction of coordinates that the two strings differ on, right? And the decoder takes y as an input and is supposed to spit out the message b. By the way, like, maybe you will never call message or represent a message by notation b in coding theory. I do it because in order to keep it like more faithful to the previous part of the talk. So eventually, like, b will remain b. Okay, so that's the reason I'm doing it. Anyway, so your goal is to take such a y and get back the message b. Okay. Now, what does the local decoding algorithm do? Well, in addition to taking the corrupted code word y as an input, it also takes a single index or bit of the message. Okay, and you should think of it as like, I don't care about decoding. At the moment, I don't care about decoding the whole message. Just tell me what the ith bit of the message was. Okay, that's the local part. I only want to, like, decode one bit. The decoder, of course, like a usual decoder can decode the whole message, therefore also tell you the ith bit. But the decoder now can do only something very simple. What can it do? It can read at most q bits of y. Okay, and q is going to be very, very small. In fact, the whole talk is about q equals 2 or 3 or 4. Okay, so this decoder is going to be super simple. It's going to read like up to 4 bits of the message, q bits of the message in general, and then based on this, make up its mind about what the ith bit is supposed to be. Okay, now notice that if the decoder once and for all decides that I'm going to query the first 4 bits or any fixed 4 bits, we are in trouble, right? Because the adversary has the budget of corrupting delta fraction bits. There is no randomness here. It's a worst case coding problem. So any delta fraction of the bits can be corrupted. So of course they can just include the first 4 bits in the delta fraction, and now you're screwed. What I just argued to you is that there must be randomness in the algorithms running. Otherwise, such a guarantee, any reasonable guarantee, is impossible. So just want to caution you, there is no randomness in the the code or like the corruption or whatever, right? Like that's the worst case problem. The algorithm, on the other hand, can use randomness. Okay, and over the choice of the randomness, over the choice basically of the q bits it reads, it should guess the ith bit correctly with advantage over half. Half is like what you would get by randomly guessing. You should beat it by like some fixed constant. Good, makes sense. I'm going to call this q delta epsilon local decoding. Q queries, delta distance, like delta is the fraction of errors it can tolerate, and epsilon advantage over random guessing in decoding. Okay, good. So that's the q delta epsilon local decoding algorithm. For this talk, delta and epsilon will be fixed constant. You can think of them as like 1%. We'll never talk about them again. Okay? Good. All right. So now, I want to talk about one more object, which is related but stronger. I'm going to talk about local correction. In order to build up to local correction, let's first observe some simple facts about coding theory. If you've taken any class, you would learn some of these facts in the first class. So none of them are difficult, okay? Now, almost all the codes we study in coding theory are linear codes. They're like maps which are linear over the appropriate field. In this case, let's say it's linear over F2 to the K, right? Or F2. So for a linear code, you can basically, without the loss of generality, assume that the first K bits in the code word are simply copying the message. Okay. In general, you can find a copy of the message somewhere, but you can just call them first K bits because the order of the messages, the code word bits is up to you. Okay. Such codes where the message appears in the first K bits are called systematic codes. Okay, that's just nomenclature. Now, what we are going to say applies even to nonlinear codes, but an appropriate version of this fact actually holds even for nonlinear codes. Okay, there are basically, some chunk of the code word bits where a constant fraction of the message has to appear, and you can prove this. Okay, so if you view it this way, then you learn that an LDC, a locally decodable code, can be thought of as taking a corrupted code word, and then by reading other bits of the code word, it can correct any of the first K bits, right? Because the first K bits are the message bits. So that's like, I can equivalently think of it as correcting any of the first K bits. Once I put it this way, you could ask, well, why should I restrict only to correcting the first K bits? Maybe I can correct every bit by reading other bits. That basically is the locally correctable code idea, where you want a code where this time the decoder takes an index of the code word bits, not the message bit. So it's in 1 through n instead of 1 through k. And then given such an I, it's supposed to decode, again reading by only constant number of bits of the code word, corrupted code word, it should decode the ith bit of the true uncorrupted code word, right, with more than random guessing probability. Now notice again, just to caution, if delta fraction of the bits are corrupted, 1 minus delta fraction of the bits are correct. So if I wanted to correct a random bit, I would of course succeed. But this is a worst case guarantee. I have to correct every bit. The randomness is only over the choice of the algorithm. Okay? The algorithm must succeed on each and every bit, even the delta fraction which were corrupted. Good. All right. So, local correction is clearly formally stronger than local decoding by the discussion we had just now. And I won't tell you all about this, but they're kind of important. They basically arose essentially when algorithmic coding theory was born. And then, in the context of PCPs, they were like in some sense the key tool. And if you think for a moment about it, if you've seen PCPs, it's not so difficult to understand why you need some object like this. But there are many other applications. Private information retrieval, worst case to average case reductions, distributed computation, so on, etc. Okay, you can ask me later about this if you're curious, but let's not worry too much about it. Let's assume that we all agree they're kind of nice and important objects. Okay, okay, so they're important, but do they exist? Okay, and the reason I'm asking this question is because at the birth of the coding theory, we knew that good codes exist. Okay, Shannon's 47 paper already contains a proof by probabilistic method that a random code is a good code, and in fact in 48 he proved even that random linear code is a good code. Okay, so existence of a good code, meaning like distance constant can correct constant fraction of errors or whatever, was never like that difficult, right? It was a combinatorial problem which was solved essentially at the birth of coding theory. Most of the coding theory is about explicitly constructing such codes, like finding polynomial time algorithms to find code, decode them, encode them, and so on. This question is a purely combinatorial one. Okay, even though everything we do eventually will be efficient, the question itself is combinatorial because there is no natural random model to argue that you will if you pick a code randomly from it, it will give you an LDC. So this is unlike like the usual coding theory, it's a purely combinatorial question. And that's why I guess it's more or less or more difficult or more interesting, etc. The way you can think about it. Good. So what we knew, let's say, what do we know about this codes? When do they exist? So, it's not such a big surprise that one query codes can't exist. That, seems easy. You can argue to yourself, at the back of your mind why it's impossible. So let me start the story at q equals 2. And, it's kind of interesting that 1 is obviously false, but there is a 2-query locally decodable code. In fact, there is a 2-query locally correctable code. It's very simple. You learn it in maybe second class in coding theory, but it's still kind of surprising that there is a code. Like it seems kind of shocking that 2 queries are enough, but it's true. Okay, and it's the Hadamard code. It's like a very simple code. If you don't know what Hadamard code is, it's simply like, views the message bits as coefficient vectors of a linear function on f2 to the k. And then the code is just evaluate the linear function on all possible points in f2 to the k. So it stretches k bits to 2 to the k bits. Okay, that's what the code is. And then, the local correction and local decoding is very simple for this. I won't tell you too much about it, but it basically relies on the fact that, any 2 points have a line passing through them or whatever. Okay, good. So this code is two-query locally correctable, locally decodable. And, early on, people realized that actually you can't do better, which is kind of a bummer, okay? At first, you might be surprised that it exists, but then you might be sad that it's exponential blow up. But then, you have to live with it because you can't beat it. Okay, that's quite, what this message is. And like this last of this work actually rules out even nonlinear codes. Even though this is a linear code, they prove that even nonlinear codes cannot beat this kind of a trade-off. Okay. What about q equals 3? Q equals 2 is done, so we should ask 3 query questions. Now, there is a very natural generalization of the Hadamard code called the Reed-Muller code that gives a non-trivial trade-off here. Just like you viewed the k bits as coefficient vectors of a linear function, this time you view them as coefficient vectors of a quadratic polynomial. Okay? And then, if I have k coefficients and they are like, I'm supposed to behave it as a coefficient vector of a quadratic, then the number of variables is root k, roughly. And then, if I evaluate it all on all points of the underlying domain, then it's like going to give me like 2 to the root k evaluation points. So that gives me like a code with like block length 2 to the root k instead of 2 to the k. So it's a bit smaller than Hadamard, right? And it turns out that, pretty much the same idea works. Instead of like 2 points, I need 3 points, and like that's basically it. And so, just like the Hadamard code, this is also a locally decodable and a locally correctable code, albeit with 3 queries. Okay, good. So, for a long time, I asked some experts to understand what was going on at the time, and like Zev Dwyer, my colleague, it turns out like, for a while people were thinking like, there may not be better codes than this, either locally decodable or locally correctable. But then there was like this, shocking and amazing result of Sergei Yakhanin and Klim Efremenko. I think Sergei was a PhD student at the time, maybe Klim was too. And then they proved that, there is a 3-query locally decodable code with like, truly sub-exponential length. So this function can be confusing, but you should think of it as like tinier than any 2 to the constant times log k, which means that this is tinier than 2 to the k to the epsilon for every constant epsilon. So it's a truly sub-exponential code, okay? And, they showed it exists. It's like a very cool result. Good, but this is a 3-query locally decodable code, and they didn't know whether this particular code itself could be 3-query locally correctable. Like they could decode or correct the first k bits, but they did not know what to do with the remaining n minus k. And so, the question of whether this code is a 3LCC was asked in this monograph that Yakhanin wrote later on, like summarizing these developments. And in particular, like no better code than Reed-Muller was known, in terms of local correction. Okay, good. On the other hand, like you could ask, okay, we this kind of a gaps are appearing now, so we can ask like, can we prove lower bounds? Can we at least show that, any locally correctable code or locally decodable code has to have like some block length, right? Like what's the minimum block length it needs to have? And it turns out that we can rule out that there cannot be a linear blow-up code. Okay, that's at least saving grace. And the best known lower bounds, this is again 2023, was quadratic. You can prove that n needs to be at least quadratic in the message length in order to get like a 3-query locally correctable code or even a 3-query locally decodable code. Good. Yes.
Maybe I'm confused. Naively, if I want to go from an LCC to an LDC, isn't the number of queries like the product of the two?
LCC is more general. So LCC is already an LDC.
LDC means I have to recover a bit of the original message.
Yeah, but like the message is basically, you can just think of the first k bits of the code word as the message. You can just, without the loss of generality, assume that your code is systematic. So LCC is just a more general object. Yeah. Is that
a general truth that I can always make code systematic?
For linear codes, it's just always true. For nonlinear codes, you have to think a little bit, but basically there is an analogous fact that is true that it's not exactly it, but essentially it is. Oh, so appending is tricky because you have to give, like if you increase the bits, you have to give me local correction algorithm for the additional bits you add to. It's not just a question of like extending block length. It's not, yeah, like, because you have to also give me a local algorithm. Yeah. As in like some more thought is required for how to do that. But I think you don't have to because it's systematic.
bigger method of making systematic doesn't work.
Yeah.
But you're saying that any LCC...
any linear code is like without loss of generality systematic, right? Like for example, think about Hadamard code. There's a linear function that computes all the bits.
Convert it to systematic and therefore also without much loss of
so that statement by itself is false, but there is something which is close enough that is true, which suffices. Basically, you can't get all the bits, but you can get like 90% of the bits. For the and the whole problem is non-linear codes. For linear code, it's just true. Okay, good. All right. So, complexity theory and coding theory is a very introspective field. So if we fail for a long time, we then think about why we are failing. And so people, that's what they did. They had like introspective results about why we are failing. So they showed that, there were kind of barriers to, why we are failing to improve these results. And there were two kinds of barriers. One is that one kind of barrier showed that the kind of lower bound methods that we had, so they suspected the lower bounds are weak. And they said that the lower bounds that we have actually apply to more general objects for which they are tight. So this is how they characterized the failures, and there are a bunch of works of that sort. And another kind of work that people showed is that actually understanding whether Reed-Muller code, for example, is an optimal 3-query locally correctable code actually amounts to settling a wide open conjecture in combinatorial design theory called Hamada's conjecture. It's like, some super sweeping conjecture about what the structure of, optimal algebraic, what's the optimal algebraic rank of a combinatorial design, okay? And so it's like known essentially in like some few finite cases. It's open essentially for all of them. And then this very nice work of Barko, Lishai, and Weinreb, they showed that the conjecture that Reed-Muller is an optimal 3-query locally correctable code actually would imply that Hamada's conjecture is true for the next case, which is actually people have been trying since like 90s, and they failed. They say, okay, this seems difficult because of this. Okay, so that's like the summary of what we know. So I can now tell you what we can do, and like all that we can do is because of the method that I told you in the previous part of the talk, okay? So first we can get a better lower bound, like we can get this k squared to k cubed. Okay, on the one hand, it doesn't seem much because, it's very far from these numbers. Now, on the other hand, maybe there is something to rejoice given that, it's some polynomial factor increase, okay? So it's like, we've developed some muscles, if not any actual benefit so far, okay? All right. And then, we try to simplify and clarify this proof. So there is a nice paper that we have with, I should not say my own paper is nice. There's a paper that we have with I write the proof a lot, but there's a nice proof that we have in this paper with combinatorialists like David Munha-Correa and Benny Sudakov, where we give a fully combinatorial proof, of the same result for linear codes. And we make this connection to the so-called rainbow girth problems, which is a different talk. In fact, I talked about those connections last week. There is a recording, if you can watch that one. Okay, so and then recently we managed to get analogs of these results for arbitrary Q. So basically the story was that there is an analog of these results of Katz-Trevisan, Goldreich et al. And Kernadis-de Wolf that actually show good lower bounds for even Q, but for odd Q they were all basically in some sense suspected to be not sharp. And then we kind of actually prove a better lower bound for all odd Q. So this can be thought of as the first interesting case, Q equals 3, but now we figured out the correct generalization that works. In fact, it's not a generalization, it's more of a realization that this was an ad hoc thing and this is the right thing. That's how I think about it. But anyway, we have some better lower bounds for odd Q, even though they look less impressive as Q increases. Okay, so I told you about this. So these all results are about locally decodable codes. It turns out that for locally correctable codes, we can actually use this technique to prove something, surprisingly stronger. So, previously the best lower bound, whether you were an LDC or LCC, was k square. And then after it became k cubed, the same thing holds for 3 LCC or 3 LDC. But if for 3 LCC, we can now prove that it is at least 2 to the k to the 1/8. Okay, so it's exponential. And the cool thing about 2 to the k to the 1/8 is that it is larger than this number. Okay. And so in particular, it shows that, well, in particular, this question is resolved because this cannot be a 3 LCC because it's too small. And in fact, there cannot be as small a 3 LCC as this 3 LDC now exists. So there's a separation between 3 LDCs and 3 LCCs. Okay. And, this result actually extends to all fields. So, that's what I wrote up there. So yeah, it's a separation between 3 LDCs and 3 LCCs. it shows that the specific codes that gave the sub-exponential and 3 LDC is in particular not a 3 LCC. And it suggests that at least qualitatively, Reed-Muller is kind of more or less the best you can do. There's of course a gap in the exponent, but at least qualitatively you're matching the behavior. Okay, so now, I'll be very short about this, but like that was last year and there's a lot that has happened since that time. So this 1/8 was improved to 1/4. And in fact, Tal Yankovitz, he's like an amazing PhD student, he just understood our proof and realized that we are being like sloppy with like one important step. And he figured out like the right way to do it. It's actually this approximate regularity step that appeared in the previous part of the talk, and he found out the right method to do it. And he immediately improved this 1/8 to 1/4. It's like amazing. And then, there's a different kind of proof that Omar Al-Rabia and Venkat Guruswamy invented. They basically, for binary 3 LCCs, which are linear, they get like essentially to the root k up to this log k factor, which is amazing. Like it's very, very close to getting the right answer, at least for the binary fields. But unfortunately, their stuff doesn't work even on F3. So like it's a great question. I mean, amongst the many questions I can ask you, one question would be, can you extend or find a correct analog of Al-Rabia Guruswamy that works for F3? Okay, we don't know. For F3, like still the best lower bound is, basically Tal Yankovitz. Okay, and then, by the way, all of this stuff is like joint with my student Peter Manohar, who is now a postdoc. So, in this same, I guess, yeah, in this paper, in the same paper, we proved 2 new results. We first proved that, the same lower bound extends to nonlinear codes. So, earlier we had it for linear, but now we can prove nonlinear. And actually, somewhat interestingly, we showed that if your 3 LCCs have a special structure called design, which is what the connection of Barkol-Ishai-Van was to this Hamada, then actually, it turns out that our technique works much better than we expected. We can actually just prove that, the answer is 2 to the root k up to like this 2 root 2 factor. So, like this conjecture that we were afraid of actually, is maybe not that difficult. Actually, basically, we just proved this Hamada's conjecture up to this 2 root 2 factor for this new case that, that was earlier people's reasons to like suspect that this problem is hard, but it turns out maybe the Hamada's conjecture was not that hard. Okay, so cool. Okay, so that was the set of results. I want to tell you, I want to tell you how like this previous stuff I told you relates to, proving such results. So I want to tell you about like the technique for proving locally decodable codes lower bounds. Okay, so that's what we will do next. And then, towards the end, if there is time, I'll try to tell you about how you can do LCCs and try to get to this polynomial concentration bit. Okay, let's start with like 4 LDCs. I'll do 4 like I told you because 3 is odd, and so 4 is like clearer in terms of exposition. And so for 4, the right lower bound, the best lower bound that we know is still quadratic, unlike for 3 where it's cubic. So I'll prove a quadratic lower bound for you for 4 LDCs. And I'll do it in the way that I promised you. I'll like reduce 4 LDC lower bounds to basically a family of XOR formulas being satisfiable, and then like pick a random one and make it unsatisfiable and so on. Okay, that's how I'll do it. Good. Okay, so that's like coding theory for you. And like what we're going to do is first observe so we have to somehow associate this 4 LDC lower bound problem to some 4 XOR problem. Okay, there's going to be some 4 tuples. Which 4 tuples? So in order to bring this, I'll observe some structural results about the decoder's action. And these results are actually very easy to prove. You can think of them as like, kind of simple cleanup steps that you would do to a decoding algorithm and show that it can be put in a simple natural form. And this was done already in the very first work that started studying them carefully, Katz and Trevisan. Okay, so I'll just argue to you and briefly sketch why it's true. So without the loss of generality, we can assume that the decoder is non-adaptive. What does that mean? Like in principle, the decoder could query the first bit, then look at the answer, and based on the answer, decide what to query the next bit and so on. But it turns out you can basically just assume that it just chooses the 4 bits to query just in the beginning, once and for all. Why can you do this? It's very easy to observe why this is true. Like the way to think about it is like, you imagine you had an adaptive decoder. Okay, you guess the queries and their answers to it. Okay? You don't ask the questions, you guess the answers. Okay, if you guess the answer, you can decide yourself what the next queries are, right? And then you look at the answer that your the decoder actually gets. If the answer agreed with your guessed answers, then you basically do what you want. Otherwise, you ignore. Okay, And I claim that this is a non-adaptive decoder that basically loses a constant at the advantage, right? Because I'm going to guess the right answers with like 1/16 probability. Okay, so I lose some 1/16 in the decoding advantage, but up to that, there is no loss. Okay, does it make sense? If it doesn't make sense, trust me. Okay, good. So next, let's just focus on linear codes. For linear codes, I'm not going to argue, but maybe it's not so hard to assume that the decoder can also be assumed to be linear. It's not in principle, it's not immediately obvious why, right? Like if my code is linear, perhaps my decoder can still win by being non-linear. But it turns out not to be true, okay? It turns out that you can basically assume that the decoder does the following. Query 4 bits of the, like to decode, let's say first bit, query some 4 bits of the code word, add them up, modulo 2. That's what linear code means, linear decoding means. Okay, this turns out to be without the loss of generality. Excellent. Finally, you can assume that if I were to apply the decoding algorithm on an uncorrupted code word, meaning like there is no error, this is kind of a no-brainer, but you can prove that it actually the no-brainer holds. The no-brainer condition says that if I apply the decoding algorithm on an uncorrupted code word, then it succeeds with probability 1. Okay, if there was no error, then you don't make any error. Okay, it seems kind of obvious. It's definitely true for linear. Actually, it's not true in this form for non-linear, but let's just focus on linear for now. Okay, good. Okay, so now let me argue the last condition. You are with me so far. The decoder's action so far that we have discussed is non-adaptively guess 4 bits, take their answers, add them up. That's what the decoder is so far. Now I'm saying that you can further assume that if I'm decoding, let's say the first bit, the 4 tuples that I query are going to form a matching in the sense that no variable occurs in more than one 4 tuple. Why? Well, you should suspect something like this has to hold. Why? Because if you overly query some single bit, then you are basically hinting to the adversary that they should corrupt that bit because that bit is more important than the others. So you expect that all bits have to be equally important. Okay? And now if you've ever seen why if I write down, so all bits being equally important, roughly speaking, is like the LP for matching. Last how many minutes? How back do you want me to go?
I mean, item 4.
I'm there. Yeah, I am discussing that. Okay. So I'm trying to argue that if I'm trying to decode, let's say the first bit, then the set of 4 bits that I'm querying essentially have to be disjoint. Okay. So I'm trying to argue why this has to be true. I'm saying, first of all, you should not find it surprising that the decoder better not query any single bit more times than others. Okay. This is like the LP constraint you have in your matching. Okay. Like every variable should, have degree, like, remember the LP you write for maximum matching? Every, let's say perfect matching, like, the degree of every vertex in the LP solution should be 1, right? And then that, for bipartite matching, you can like round the LP and get an actual thingy. It turns out that actually for any other graph, you can also round it and get a half approximate solution. Actually, for even a hypergraph, you can do it and get some other constant approximate solution. Okay, that's pretty much it. By just starting from the case, and this, I did not give you a complete argument, but like that argument applies. Like I'm saying that, if you have a hypergraph where all vertices appear with like roughly equal frequency, then you can like, basically do this LP rounding and get a matching out of it and lose some other constant. That's it. Okay. So you can basically assume that the decoder is the following simple object. I have a bunch of matchings, one for every bit that I'm decoding, right? And the decoder's action is, if I want to decode ith bit, query a random 4 tuple in ith matching, add those bits up. Okay. All good? Good. Excellent. So now, our argument actually gives omega n size matchings. Maybe I did not tell you why. Let me argue why. The matchings must be omega n size because if they cover little of n vertices, if they don't cover like constant fraction of the vertices, then notice that, I can corrupt all of the variables involved in that matching. I have a budget of delta n, right? An adversary can corrupt delta n things. So the matchings better be of size bigger than delta n. Otherwise, I can corrupt all those bits. And so the matchings must be of size in general, like, omega of delta n. But let's assume for the purpose of today's talk that they are perfect matching so that I don't have to carry an extra parameter. None of what I do will actually use this too strongly, but this will just reduce one extra parameter. So because, if you are doing Q query locally decodable codes, I'm just going to assume that the matchings are all of size n over q, and n is divisible by q, and so on. Okay, good. Any question about this cleanup? Okay, great. Now, the same kind of description applies to local correction too. Instead of one matching for the first k bits or the message bits, you have one for every one of the n code word bits. Not a big surprise. Everything else remains the same. Okay, great. So now let's do like this reduction that we were discussing. Let's reduce 4 LDC's existence to, this satisfiable XOR formulas. Okay, so the XOR formulas will simply encode the following clause, which I'm first going to describe in words, and then I'll write down the notation for it, okay? There'll be one formula for every possible message. So if it's a k bits to n bit code word, there are 2 to the k possible messages. I'm going to give you 2 to the k different formulas, one for each possible value of the message, okay? Given a message, the formula encodes the following, statement. There exists a code word X, namely, the encoding of that message, such that if I apply the local linear decoding on X for decoding the ith bit, what is the local linear decoding for decoding the ith bit? Well, go to the ith matching, take any I tuple, and add the corresponding bits. You should get back the the corresponding message bit. Okay. Basically, that's what it is. That's what the clause is. Okay. This is if I apply. There is a code word X, was that if I apply the local decoding for any of the message bits, then it succeeds with probability 1, and it should succeed with probability 1 because I'm applying it on uncorrupted code word. Okay, so let me write this in notation. Here's the notation. For every B, there is one formula. For every message, there is a formula. Let's call that formula psi sub B. In psi sub B, what does it do? It goes through all possible matchings, one for every message bit. It goes through all possible tuples in the corresponding matching for all C in HI. And then it says, I've gone to the plus minus 1 world. This is not surprising. That the product of the bits, which is addition mod 2, so product over plus minus 1, equals the corresponding message bit. And now you can see why, B is the message. It's done to resemble the KXOR thing that we had before. Okay, so you're all with me here. For every B, I have basically, so each matching had n over 4 elements. There are k matchings, so I have a system of nk over 4 XOR formulas, right? One for every possible message B. And notice that, for every B, the corresponding formula is satisfiable. The satisfying assignment is simply the code word corresponding to that B. You're all okay with this? Yeah? Cool. Any questions? Okay, great. Okay, so now we have a very natural definition of a random formula. A random formula is pick one at random from this family, which is same as pick B at random, right? And okay, so take a random B, look at psi B and try to prove it's unsatisfiable. Okay, so we'll prove that if k is too large, it is unsatisfiable. Therefore, k must be smaller compared to n, or n must be large compared to k. That's our strategy. Good. Now, notice, as I reminded you earlier, the number of random bits in the choice of this formula is basically the number of message bits. We are in coding theory. Of course, the number of message bits is much tinier than the number of code word bits. Okay. So that means that, the number of random bits is much tinier than the number of variables in the formula, because the variables in this formula are one for each possible code word bit. Okay, you're all good with this? Okay, great. All right, so now, let's apply the stuff we did earlier in order to prove this random psi B unsatisfiable. Okay, so, what we're going to do is for this. So, I guess I'm just repeating myself, but we know that if there is a 4 LDC, then every one of the psi B's is satisfiable. But we'll show that for a random B, psi B is unsatisfiable if k is too large. Okay? And then we have a lower bound. Okay. So notice that psi B can be written in this following way, and I'm trying to now match the notation from the previous part. Okay, in order to get to a point where we start looking at the kind of technique we were looking at from the last talk. So how does my psi B look? So I'm going to look at this advantage polynomial, just like we wrote down for the 4 XOR formula earlier. But this time, if I look at any C in HI, all those corresponding monomials, they get multiplied by the same BI. Earlier, we had like a B sub C, one for every C. This time, we have the same BI multiplying all these n over 4 different constraints coming from any single HR. It is what it is, so that's what we wrote down. Okay? And we have to prove that, this formula, psi b of x, we have to prove an upper bound on this for a random b over all possible xn plus minus 1 to the n. Okay, so yeah, this is what we know, that if it's a LDC, then it is large. On the other hand, we'll prove it's small, and then, we'll be happy. Good, okay. So, just like before, we'll write it as a quadratic form of a matrix. What matrix? Oh, it's a 4 LDC. Let's, we know it's a 4 XOR formula. We'll do the same Kikuchi matrix from earlier, right? So this is the matrix, you all remember. We'll look, we'll choose a parameter L. We haven't decided what L is, but let's work with it. It's the same matrix that we saw from the previous part, like, the matrix for ith. So, I'm going to include, so, I want to collect a matrix where BI would multiply. Last time I collected only a single hyperedge, but this time BI multiplies all hyperedges that come from HI. So I'm going to collect all the edges corresponding to the ith matching in a single matrix. That's what this AI is, okay? So what does this AI's edges look like? Well, S and T have an edge if their symmetric difference is a 4 tuple that lives in HI. Okay, there are n over 4 tuples. Any of those is fine. Okay? Still good? Okay, great. So, let's just do the same kind of computation we were doing earlier. How many edges in HI? Well, each C contributes exactly the same number of edges as we looked at last time because there is no difference. Okay? But, in AI, we are collecting together the contributions due to n over 4 different hyperedges. So the total number of edges in AI is n over 4 times delta. Okay? Sounds okay? Okay, great. So in particular, we can compute average degrees of AI because we are going to need it. So let's compute them. What's the average degree of AI? Well, this is the total number of edges. Total number of vertices is n choose L. Okay, so let's just do this computation. Remember, this is supposed to be L square over n square. Up to constant, it multiplies n, so I get L square over n. Okay, so we just like designed this matrix, we were able to compute what the average degree of every AI is. Okay, excellent. So that's where the situation stands. Okay, so now, let's do this quadratic form computation from the last time. Again, you're not so surprised. This quadratic form basically up to a scaling represents psi b. We know the scaling is exactly of this delta, the number of times each C repeats. So, this formula is not that surprising, right? So, we know, that this quadratic form is like a delta scaling of basically the ith matching's contribution to psi b. Okay, so now we can start doing this computation. This is like basically we collected together all the facts we need here. We're going to do the computation from the last talk, but just for this formula now. Okay, so this one is a lower bound that holds if I start with a 4 LDC towards a contradiction. So assume there is a 4 LDC that maps k bits to n bits. Okay, so I know that it has nk over 4 total number of edges, n over 4 in each matching, k of the matchings. Each edge appears delta times, so that is the total number of edges. And because every constraint is satisfied by the code word, if I were to plug in psi b the corresponding code word for b, I would get 1 for every possible monomial. There are kn over 4 times delta monomial, so that's the lower bound, okay, for every b on psi b. On the other hand, I'm going to take a random b and take expectation over like this quadratic form now. Okay? So because this inequality was true for every b, it's true also in expectation. So this inequality holds. Now, I'm going to write, so this is a quadratic form. What did I do? I took x circle L. I took the L2 square norm of x circle L and pulled it out, the spectral upper bound. Okay, I'm calling that number n. Like n is just n choose L. Okay, you're still good? Now what do? I apply the Khinchin inequality. I say that this is n times the variance term, sum I ai square to the 1/2 times square root log of the dimension of the matrices. The dimension, remember, is n choose L, so this is square root log of n choose L. Okay, still good? Okay, so now, let's consider, what we want to like understand what this term looks like, right? So let's consider what the spectral norm of AI is. AI is a adjacency matrix. Okay, it's a 0, 1 matrix. its spectral norm is the largest degree of any vertex because it's a graph. Okay. So I said, okay, AI's spectral norm is at most the maximum degree of any vertex in AI. Okay. So if AI spectral norm is at most D max, then AI square spectral norm is D max squared. I'm summing up k things. By triangle inequality, the spectral norm of this guy is at most k times d squared, d max squared. And then I took the 1/2 part. Okay, still good? They're all like, all I want you to observe is that they're all like simple upper bounds. We are doing nothing complicated so far. Okay, and we're never going to do anything complicated. Okay, so that's the upper bound we have come up with, right? So, all I did here is like I canceled the square root k. Okay, and I took this capital on the other side. Okay, why am I doing this? Remember in these two applications we saw before, we arranged an expression to get d average out. That's what I'm doing here. Okay? All manipulations are the analogs of the manipulations we did earlier. So, we're going to observe that this is d average. Why is this d average? It's n over 4 times delta, total number of edges divided by number of vertices. That's the average. So we basically have that d average times root k is at most d max times root log n. Okay. So, I just rearrange and square both sides to get k is at most d max over d average squared times log n. You're all good with this? So we have gotten an upper bound on k. Okay, and notice that it was just a complete black box application of matrix Hinchin. Nothing very difficult happened. So now, we have to do the same trick that we pulled in all the applications earlier. We have to make d max and d average comparable so that we can just like call it 1 and go away. Okay. So, if AI is approximately regular in the sense that all the degrees are roughly equal, then d max and d average are equal. In that case, the lower bound we'll get would be, or the bound we'll get will be k is at most log n. Okay, log n is like log of n choose L, so that's L log n. Okay, so I want you to remember this as saying that k would be at most about the level of the Kikuchi matrix you use. K would be about L. Okay, if AI was approximately regular. Okay, this is just observing what happens from this inequality. Now, let's observe this statement about the average degree of AI. Okay, average degree of AI is L square over n. We had discussed earlier, and I repeat again, if the average degree is less than 1, you simply cannot be approximately regular, right? Because there are some 0 degrees. In order for approximate regularity to even be sensible, we need average degree to be at least 1. So L square over n needs to be at least 1. So L needs to be at least square root of n. Okay? So, it seems like, I get a better lower bound if L is smaller, but the lower bound doesn't make sense unless L is at least root n. So the L I should use should be root n, and I get k is at most root n, or n is at least k square. Okay, and now that was a necessary condition that L be at least root n, but it turns out this again is a Chernoff bound argument, and it comes from the fact that HI was matching. Okay, that if I choose L to be about root n, then not only the average degree is 1, but only a negligible fraction of vertices have a degree which is much larger than 1. Okay, in order to convince you that this is not a hard thing, let me give you intuition. What does it mean that the degree of a vertex is large? A degree of a vertex is large if there are multiple 4 tuples that give you an edge on the same L tuple. But these 4 tuples are disjoint. So each time a 4 tuple gives you an edge on some S, it has to block 2 more choices that I had in picking S. If I pick one C, like you told me which pair is there, and then if I tell me one more C, then 2 more things are blocked. So notice that if I try to increase degree of S, I have lesser and lesser independent choices. Okay, so the fraction of S's that will satisfy them will be small. That's the intuition. Okay, and you can make this argument very formal by Chernoff bounds. So that's pretty much it. Okay, so approximate regularity is basically guaranteed as soon as the minimal condition for it is met up to some logs. So you get k is at most root n up to logs. Okay, so that's what we have proven. Okay, any questions so far? All I want you to observe is that it was a situation with a lot more correlation than even the one we started with, where we were a little bit worried about correlations to begin with. But then we just repeated the same argument and we got blocked nowhere. Right? We had much fewer bits of randomness in this argument than the previous one. In the previous argument, we had one random bit per hyperedge. This time we had one random bit per matching. Okay? In particular, the number of random bits was tinier even than the number of variables. But the previous argument was so robust that it did not care. We just repeated the whole thing. There was only one combinatorial place where we had to care, which is average degree. And then we just figured out what average degree to use, and that's it. Cool. Okay. So it seems like I have, I have 17 minutes and 50 seconds. So I am going to tell you about LCCs a little bit, as in like 10-minute version. And then I'll tell you some 2 or 3 out of like a long list of open questions. Okay, that's my plan. But let's do a little bit of a postmortem of this argument that we just did. Okay. By the way, we should not get too happy. What we just proved is a result that was known since 2004. Okay. All I did for you is give you a particularly simple proof of it, but there is no improvement in this. Okay. But the upshot is that there is a version of this argument that does give you the cubic argument, cubic lower bound for 3 query codes, okay, where you have to do the odd thing a little bit more carefully. Okay. Regardless, we proved, this lower bound. And remember in our argument what happened? We said in the best case scenario, Dmax and Daverage are comparable. And then K is at most log n. So the best lower bound we get is like the level of the Kikuchi we were at. Right? I can go back to the previous slide to make this point again. Remember, this is the thing we got. We said, okay, if we are approximately regular, then I can make this thingy 1, and then K would be at most log n. And then in that case, the lower bound, the inequality I get, the bound on K I'll get is like L, the Kikuchi level. I want a tight upper bound on K. So I should use the smallest level. But then I was blocked because I need to use a level at which Dmax and Daverage can at least have a chance of becoming comparable. So you can think of this as, to get a better lower bound, to have a chance for a better lower bound, one could think of the goal as trying to design some matrix where the average degree of AI is at least 1, like the minimal density condition, that this condition should be met at as low a size of the matrix as possible. Like this is our design constraint. Right? We designed some matrix here and that gave us this, but in general, like this is our goal. Right? If we could somehow make this happen at a smaller size, we would get a better lower bound. Okay, good. So let me tell you about this, with this, learning in mind, let me tell you a little bit about this 3-query locally correctable coarse lower bound. Good. Okay, so let's see. I'm switching gears now. It's the very last part. I know you are tired, but we're gonna be done soon. Okay, good. So remember the LCC setting. There's only one key difference. I have n matchings instead of k. Okay. Good. So at first it looks better because remember our whole goal, our whole learning was that we need to create denser matrices. Right? Denser matrices would happen if I had more constraints. More constraints would happen if I had more matchings, which seems like going in our favor here. I have more matchings, so more constraints, so hopefully more I can create denser AIs at lower levels and then maybe get a better lower bound. That seems fine, right? The issue, of course, is that only the first K matchings come with a random bit, right? Because there's still each formula is decided by the message. I don't have a ability to pick 2 to the n random. I don't have a ability to choose n random choices. I just have K random choices. So basically the bottleneck in the previous lower bound ideas was that even though there are this extra n minus K matchings, we didn't know what to do with them. So all the lower bound techniques, what they did was they thought, well, forget about the n minus K extra matchings, use the K and then whatever happens, happens. So let me now show you how you can actually use the n minus K additional matchings and get some win. Or at least let me tell you how you can do this at a high level. Okay. So we try to reduce this 3 LCC problem to the family of XOR formulas just like before. So I wrote down the new, so these are the old constraints, which are for the first K matchings, which are exactly the same as before, which should not be surprising, right? Because it is basically the local decoding constraints, right? The first K bits are simply the message bits. But then there are additional constraints. Right? What do these additional constraints say? It says that, if let's say, I go to K plus 1th matching, or let's say nth matching. Okay, this is not like one of the systematic bits. It's like a code word bit. What does this constraint say? It says that, if I take any triple here, I add those bits up, then I should get the nth bit. That's what it says. That's what this constraint says. Like, if I go to every one of the matchings in the last n minus k, take any tuple in one such hi, then if I add those bits, so this product in the plus minus 1 world, I should get the bit corresponding to the matching label back. Okay? So we have more constraints, but the issue is that the random bits only are on the first nk over 3 constraints. Even though we have like n square roughly constraints in total, only the first nk constraints, roughly speaking, get a random bit. Okay? Do you all agree with this? Do you all see this? Okay, great. So, the same kind of fact that was true for LDCs holds true. Like, for every B, the system is satisfiable, namely the code word of it, and so, our task is still the same. Pick a random B and show it's unsatisfiable. Okay? Good. So now, what we want to do, so, we have this extra n minus k matchings which are giving us more constraints. Okay? What we want to do is use them to create additional constraints with right-hand sides BIs. Like, we needed these constraints with right-hand sides BIs, but we didn't have them. We only have the nk of them. Now I want to create more constraints with right-hand side BIs by somehow using this information from the remaining n minus k matchings. This is like some manipulation I want to do to the system of equations I have before applying this whole machinery that we developed. Okay? And the manipulation is very simple. Here's what I'm going to do. I'm going to pick one of the first k matchings. It gives me a constraint of the form x sub c is bi. Okay? Then I'll take another constraint from one of the remaining n minus k matchings. It gives me a constraint of the form xc prime equals xj. Right? And then what do? Well, if these two equations hold, I can multiply, the left-hand sides and the right-hand sides, and I get a new equation, right? So the product of xc and xc prime should be equal to the product of bi and xj. And then, I can move xj on the left-hand side because xj square is 1. That's what this is. Okay? I'm going to call this a derivation. It takes two constraints and gets like a new constraint out. In this new constraint, let's understand why or when this can actually help. Okay? Now, here is the part that is working against us. The new constraint, we started with a constraint with like 3 variables on the left-hand side. This new constraint has more number of them, right? Like it has c and c prime and j. So in general, the number of variables in the constraint is rising. Okay? Why is it bad? Like in some sense, if the arity of XOR instance rises, there is like, the thresholds for refutation, etc. increase. That's not in our favor. Okay? On the other hand, so let's try to understand how does the trade-off work in this case. Suppose the total number of constraints we derive with the same RHS, let's say b sub I is some number mi. Okay? Now, if you go back and do the same average degree computation, in the previous thing, remember it was L square over n square times n. Okay, the L square n square over n square came from n choose L minus 2 over n choose L, and then we said there are n over 4 elements in a matching. The n over 4 is replaced by mi because they are like mi constraints with bi as a right-hand side. Okay? And the L square over n square was really L over n to the q over 2, where q was 4. Okay? So if the arity of this new constraint is q, then this is like the average degree is going to look like L over n to the q over 2 times mi. Okay, this is the exact same computation, we just did it with this. Okay? Now remember what our heuristic is. We have to somehow make this number larger than 1 at a smaller L. So when do we win? I mean, at least in this heuristic sense, we will win if I can have a large enough mi to more than compensate for the increase in arity, so that the effective density becomes 1 at a smaller level L. Okay, so that's hope number 1. We have to somehow create a scheme of these derivations and argue that no matter what these matchings, I will be able to derive enough constraints with right-hand side BIs so that the average degree of any AI becomes bigger than 1 at a lower L. Okay? Now, of course, this is just a heuristic, this is a sanity check. In the end, remember, we need this D max and D average to be comparable. So far, our arguments for this were just based on them being matchings. Like I gave you this heuristic argument, like the tuples were disjoint. Now they're not going to be disjoint, right? Like I'm using like all kinds of like other elements, and they're going to intersect. Okay? So, you know, if roughly speaking, if I overly use some variables, then you can show that, you know, the degrees will start becoming lopsided. So, you know, I have to somehow not only find a derivation scheme where mi is large, but I also have to make sure that the new constraints I'm getting are well spread. They don't overly favor a single variable. It seems sensible. They should be matching like. Okay, they cannot be literally a matching, but they should be matching like. So these are our two choices. We have to find like a scheme of derivations that on the one hand has a large enough mi, and on the other hand is also well spread. Okay, and it turns out that there is like a simple scheme that actually does work. And you know, the idea, I won't tell you much about it, but and you can ask me later about it. It's called chain resolution. I'll tell you what, you know, if you ask me, I'll tell you, but I'll skip it for now. And you know, in some sense, you can show that if you do this chain resolution, then you know, the heuristic works out very easily. And not only does the heuristic work out, you can also work out approximate regularity in the case when the matchings are random. Okay? You can think of this as like, you know, some well spread case. Okay? But arguing that this well spreadness is without loss of generality is somewhat trickier here now. And you know, you use like slightly more complicated structure versus randomness argument to show that it is without the loss of generality. In some sense, everything that we did in the previous applications works out, just a little bit more work. Okay? Now, just to show you where this polynomial concentration plays a role, it is, you know, like when the matchings are random or well spread, you have to argue that there is no lopsidedness in the degree. Okay? You know, earlier we could do it by Chernoff bounds because basically the events that different C's are intersecting with a C were disjoint. But now they intersect. Okay? So it's no longer a linear problem. It's no longer like a Chernoff bound problem. It instead becomes a polynomial concentration problem. Why does it become polynomial concentration? Well, because if you think of the degree of S, right, the number of C's, number of pairs of C's that give me an edge, it's going to look like, you know, some polynomial of degree q over 2. Okay, I won't describe too much more, but like hopefully it's not that difficult to see. Like I'm saying, like, you know, this condition that xs should intersect, you know, some number of constraint is like some q over 2 degree polynomial because it's a condition on q over 2 different variables. Okay, it's some non-negative coefficient polynomial, and you need to understand, like, you know, is it well behaved? We want to understand, like, you know, is it typically near its average? This is where like this idea from earlier plays a role, that well spread polynomials actually, you know, do have Chernoff like behavior around their expectation. Okay, so we basically, the idea is, so I'll show you this polynomial concentration, but I'll just finish the high level description of this technique now. The idea is that you formulate some appropriate well spreadness condition for these matchings and show that under that well spreadness condition, the polynomial concentration fact tells you that it will behave typically as its value will be typically around its expectation. So there'll be some outlier rows which are too large, but typically, like, you know, most vertices will behave as if they are near the average. And so this gives you approximate regularity for the well spread case. You can argue that the random matchings case will be well spread. And then you have to somehow show, like, you know, what to do when the well spreadness doesn't hold. I won't tell you much about it, but there is some work required to understand what happens when the well spreadness doesn't hold. Okay, that's the whole scheme. In order to give you one takeaway which is very important, I want to show you this polynomial concentration inequality. In fact, I just want to tell you one corollary of it because you can remember it without ever remembering the parameter details. If you actually go back and read the papers, somehow, you know, they have a scary looking form, but like this particular message is very simple. So I want to just like leave you with it. Okay. Okay. So in order to like show your form, let's recall like the Chernoff bounds. Hopefully you all remember this. If x1, x2, xn are Bernoullis, independent Bernoullis with parameter p, so 0, 1 random variables with chance of 1 being p, then, you know, the probability that some xi is 1 plus minus mu is, you know, 1 minus some exponential, right? And the exponential's behavior is controlled by the mean itself, right? You all know this Chernoff bound. So, you know, two things to note. Some xi is a non-negative coefficient polynomial. All the coefficients are in fact 1. And moreover, all the coefficients are equal. So no variable is much more important than another. Okay? Those are the two things we'll remember. And I'll now give an inequality that generalizes this to higher degree polynomials. So here is a polynomial concentration inequality. Actually, such things were invented first by Kim and Wu to study random graph problems. And then like the short versions or like stronger versions of this are due to Studi and Sridenko. It says suppose P is a polynomial in X of degree D. D equals 1, you should think of the Chernoff bound. With non-negative coefficients, just like this. And now, I want to understand what is the right analog of the condition that all coefficients are equal. One way to think of what happened here was like if I take any partial derivative, there is only one to take, then all the partial derivatives have the same expectation, namely 1. Okay? That's what basically this condition says. It says like if I take any partial derivative of the polynomial and then take the mean, it should have a mean which is much tinier than the polynomial's mean. No partial derivative's mean should be much larger than the mean of the polynomial itself. Okay? Does it make sense?
This is true for any.
Yeah. No, true for every polynomial. Doesn't need to be homogeneous. Yeah, the statement is correct as stated. Yeah. Then it says that, Px, so now this is a bit of weaker behavior. It doesn't give you 1 plus minus epsilon, but it says that, the chance that you take a value which is larger than some lambda times exponentially in the degree of the polynomial times mu is 1 minus some exponentially decaying function. Okay? Now, in our application, actually we needed 1 plus minus beta for the 3 LCC lower bounds. And our polynomial, so in some sense this xd was very bad for us because the polynomial that we have eventually looks like a log n degree polynomial, like when we actually have to prove. So we proved like a incomparable but better for large degree version of this result. If you want, it's a very simple proof. It's in our paper if you want to take a look. It's a very elementary proof. So we replace this xd times lambda by just 1 plus beta to the d, and you can take beta to be 1 over d here. Okay, and then instead of like this exponential function, we lose an additional n to the d here, which in our application doesn't matter, but then it gives us like basically sharp concentration around the mean. Yeah, I'm avoiding it. I think I just assumed here that beta is 1 over d. Yeah. Yeah, sorry, I just copied it wrong. I think, okay, let's see. I think, yeah, okay, what should, yeah, which should make sense. Like okay, yeah, sorry, I guess I copied it wrong, and I think now I don't even remember what the right thing is. But I think you're right. It is going to be x beta. Yeah, I think it's going to be x beta. Yeah, I'll double check, but that's what it is. But it basically, like the message is that you can get like a stronger inequality for large degree polynomials by paying a little bit extra in this exponential function. Good. Anyway, so this is like a useful tool, and hopefully you'll find some uses of it. That's pretty much it. Do I have we just did an argument by induction on D, and like in the induction step, like so each induction step is like loses like a factor of n. So we did some quick and dirty union bound thing. I'm sure there's a smarter version possible, but we didn't care, so we didn't prove it. All I'm saying is that Kim and Wu did not care about it. For them, D was always a constant, so they never they just packaged all this dependence with 2 to the D. And then, we cared about this D, so we were worried about it, but we didn't care about the tail. I'm sure there is a stronger inequality that improves both. In our application? Yeah, sorry, I was not so clear. So, the randomness is pick a random row. Okay? So look at the degree. Like the degree function is pick a random S, which is like, it's a set of size L, which is roughly an L over n biased bit vector. And you're asking what's the chance that it intersects with a given number of pairs of tuples. No, yeah, it's for the analysis. Yeah. In the end, it's a deterministic matrix. We're just trying to account for what fraction of S's are bad. Yes, this is just approximate regularity. This is just a way to analyze how regular your matrix is. Yeah. Good. Okay, so can I get like 3 minutes extra? Okay, I want to pose like, this conjecture about improved inequality. Okay, good. So anyway, so, we are coming to the end of like this marathon session. Sorry for telling you too much. we were proving this lower bounds, and I told you that there's a huge gap between what we can prove and what we expect. In particular, if I had to conjecture, I would say that there are no 3 query codes with polynomial blow up. You should be able to prove super polynomial lower bounds. Okay, so I'm going to tell you how one might be able to prove that. Okay, good. So here is the thing we get stuck on, right? Like remember this step. We got stuck at here. We said the best thing we can hope for is like Dmax or D average is 1. Then k is at most log n, and that gives us k is L. Okay, and then we said L. So in some sense for LDC lower bounds, we don't seem to have a method to beat this, right? The lowest L at which degree of AI is 1 is what it is. Okay, so it seems like we are kind of screwed with this whole method. But let's remember where this log n came from. It came from the Khinchin root log n. Like this whole business is occurring because we just accepted the loss from the matrix Khinchin inequality. So we should ask, is that loss necessary? Right? Can we improve the inequality? So let me, pose that as a question next. Okay. So yeah, I guess they were supposed to appear one at a time. But anyway, there was a root log n loss that was like kind of the problem, right? But as we discussed, the loss may not be necessary. In the worst case, in terms of AIs, that loss is necessary. But in general, for your given AIs, they may not be necessary, right? So in fact, like such improved inequalities are an active topic of investigation in animatrix theory right now. So here is a result from like a few years ago, which is like extremely useful. Actually, this whole line of work was begun by Joel Trop, and then I think this result is actually very useful. But Trop really, in some sense, thought about this whole line of work on how to improve Khinchin inequality. In fact, like the improved simpler proof of Khinchin that he came up with in 15 was towards improving the Khinchin inequality. He first came up with a simpler proof and then tried to use it to improve it. Anyway, so here's an inequality that Bandera, Bodhihardo, and Von Handel proved a few years ago. All the same hypothesis, your symmetric matrices. I want to understand the expected spectral norm of some BI AI. Okay. Now notice what the right-hand side looks like. There was, in the usual Khinchin inequality, there's a root log n here and there is a 1/2 here, which still is supposed to be there. I'm just making the same mistake again and again. But the root log n has disappeared. Okay, they're saying that the root log n doesn't multiply this matrix variance parameter. Okay, instead it multiplies. So it turns out that they believe this log to the 3/2 is weak. They believe that the best known thing here should be best thing you can expect here is root log n. Let's give it to them. Let's assume this is root log n. Okay, then it multiplies some other parameter. Okay, which is not the variance parameter, and this other parameter is something that they call the matrix alignment parameter. Okay. Now I'll just give you like one line or 2 line brief of what this is supposed to be. The intuition is that matrix Khinchin inequality is tied. One case when it is tied when all the AIs commute with each other. Okay, when all the AIs commute with each other, they are basically equivalent to diagonal matrices. They have a simultaneous diagonalization. You can just assume that they are diagonal matrices. Okay. And if you're curious, I wrote up an example, a tight example for matrix Khinchin for diagonal matrices on the board over there. You can take a look at it later. What these inequalities are trying to get at is they want to quantify how non-commutative your AIs are. And then if they are sufficiently non-commutative, they want to say that actually you can beat the root log n in the Khinchin inequality. And so the sigma 1, you should think of it as like, some measure of how commuting the matrices are, how aligned they are, how aligned their eigenbases are. That's what it is, okay? I won't tell you what they are beyond this. Now, you could, advertisement. Okay, so unfortunately, if you try to use such results, this result or even like variants of these results, they do not work for our case. Not only because the inequalities as stated don't work, but the philosophy doesn't work, okay? And I can tell you more, like there is a reason, the results that prove this, they don't just prove these inequalities, they end up proving something about the spectrum of the matrix, the whole set of eigenvalues. And those kind of facts are simply false for the matrices we are looking at. So there's a philosophical problem with these kind of inequalities that not only they don't work, those kind of techniques are unlikely to work for our case, okay? Nevertheless, I believe better bounds are true, but the betterness, like how better and what better it is subtle. So let me make a precise conjecture, and that's essentially the last thing I'll tell you. So here is like a very precise conjecture. I'll make it for just 4 uniform hypergraphs because that's all the talk was about, right? But there is a version of it that holds for every Q uniform hypergraph. And in order to not worry too much about well spreadness, I'm just going to assume that H is a 4 uniform hypergraph such that no pair occurs in more than one hyperedge. Weaker conditions will suffice, but this is sufficient. Okay? So H be a 4 uniform hypergraph, then for every L which is not too large. Not too large means that you're not like linear or n over polylog n. Okay, so I'm comfortable making this conjecture for n to the 1 minus delta for any delta bigger than 0. Okay, then if I compute the spectral norm of the matrices that we were looking at in the talk, we basically use the bound which said root log n times this variance sum, again 1/2 missing. Okay, that's what we use. The root log n would have been this L term. Okay, and when L grows, this was a problem. In this conjecture, I'm saying that in fact the right answer should be minimum of L and n over L. Okay, I won't tell you why I make this conjecture, but basically you can't hope to prove anything better. This is the best you can do here. Okay, and there is a combinatorial version of this which I can actually prove for random matchings. So I think this is the right thing to expect. Like this is what you should expect here. If it is true, you would get arbitrarily large polynomial lower bounds for 4 LDCs and likely for any greater than or equal to 3 query LDC with some more work. We don't know any such results. In fact, we don't know any super quadratic lower bound so far. Okay, good. So that's the outstanding problem. I told you a lot about it. I won't tell you much more about it. And I'll just leave this open up here, right? We are kind of close to, but not quite done this task of settling the 3 LCC lower bounds. Even on the binary field, it will be great to do it. Ignore this second thing. It's a context I've not told you. And actually, let me tell you the last thing. That's kind of very interesting. Everything I told you today was really about like LDCs on small fields. Like, when the alphabet size or field is small, in fact, constant. Most of the applications were like that. But actually, it turns out that these LDCs are very useful objects when the field size grows. In fact, field size grows exponentially in the message length. That is a regime which is very useful. In fact, in that regime, you can design private information retrieval protocols using these things. None of the lower bound techniques invented after Katz and Trevisan's very first paper on the topic, so that goes back to 2000, yield any better lower bound. So even though there is all this sequence of works I mentioned, none of those works apply to this large alphabet regime. The best lower bound for this regime is still the 2000 result of Katz and Trevisan, which essentially started this field. It's reasonable to ask, like, can all these new developments at least give us some handle on proving a new result here? We don't have one here, but it will be a really amazing thing to get like a new technique to prove lower bounds in the large alphabet regime. Okay, good. So yeah, that's stuff I told you, and yeah, sorry for going over.
Do you have any more questions, sir? Okay, if no, so let's thank Pravesh again, and right, so